This module covers Infinera's technology leadership, but especially from the point of view of cloud-scale trends and requirements. My name is Jeff Bennett, and I'm a Director of Solutions and Technology in the Product Marketing team. Just to be clear, the module will be phrased in terms of messaging training and will be presented in the form of an internal training video. There are customer-facing versions of these slides on Smarter. Here are the 5 key learning objectives for the module. I'll be defining cloud scale and how it's evolved, helping you understand 3 key properties of the solution, namely capacity, programmability, and intelligence, defining the 3 axes of optical scalability and where to find out more, presenting the idea of a programmable optical data plane and how it's enabled by PIC technology, and laying out possible evolutionary steps towards adding intelligence, and again, telling you how to find out more about that. So let me begin by setting the scene and explaining a couple of terms. Over the past 10 years or so, we've seen a huge shift in network architectures driven by a trend towards virtualization. Sometimes people refer to this as cloudification. Now, at some point in the distant past, most of the functions in the network, such as routing or firewall or packet classification, were based on dedicated hardware. So if you walked up to a rack of equipment and you were looking for a firewall, there would be a box that was literally a firewall. It was dedicated hardware. Now, as general-purpose CPUs became more powerful, people found that things became a lot more flexible if these functions were run as software processes or virtual network functions on CPU-based appliances. That process is called Network Functions Virtualization, or NFV, and it leads to the creation of a layer or set of layers in the network that we can label the cloud services, or layer C. But if you still need to move bits from one VNF to another, well, this could be happening on tens or hundreds or thousands of kilometers of distance. So layer T becomes the intelligent transport layer that supports the operation and evolution of layer C. Now we can think of the messaging glue between these layers as being driven by software-defined networking protocols, or SDN. A key point is that the demand for bandwidth is so great that optics becomes the dominant technology in this kind of architecture. But the argument I'll be putting forward is that it's not just any old optical network. There are certain things that this architecture needs, or at least it will operate far more smoothly if you can meet certain requirements. Now, for the most part, this layer C, layer T transformation was triggered by the growth of the web giants, companies like Google, Facebook, Microsoft, and so on. Now, their web scale architecture is driven by the need to scale rapidly, and they evolve a technique called DevOps. Basically, this means that network application developers work incredibly closely with the network operations architects to ensure that capacity is delivered at the right scale and at the right time. Web scale means very linear topologies and very large network flows, so-called elephant flows. Elephant flows start and end in the same place, A to B, and they don't need multiplexing or switching in the network. They just need bandwidth, and on a massive scale. They're looking for a network that's scalable, disaggregated, and open. But let's not forget the classic telecom operator. Not just the tier 1s, but the competitive operators and the wholesalers. They're delivering cable, mobile, and fixed broadband services at an increasing data rate. The topologies are very meshy, and they consist of millions of tiny, or mice, flows. They're looking for a network that's sliceable, it's got integrated switching and grooming, it's highly secured. But guess what? Their evolving architectures are also becoming more cloud-like. And so, we see the idea of cloud-scale architectures demanding all of these properties from the same network architecture. In particular, this cloudification is extending outwards. So we don't just see the classic mega data centers anymore, but as fiber pushes deeper into the metro, we see small data centers popping up in the next generation cable architectures, known as DAA, and in the migration from 4G to 5G mobile networks. But what does this new metro network architecture have in common with core networks? Well, it's really about the need to scale capacity and have the fastest possible response time to deliver that capacity. Those needs are driven in the metro because there's just a huge number of endpoints, and each one feeds into the new fiber-deep architecture. In the core network, we need much bigger chunks of capacity with much less notice because this is where all the traffic is aggregated. Those are the high-level trends we see as most relevant. So, what are cloud-scale network requirements and how do we satisfy them? Well, I'm going to break these down into 3 factors: maximizing capacity in the optical network, enabling programmability, and adding intelligence. And I'll start with maximizing capacity. When we think of optical scaling, we're actually trying to achieve a number of objectives, although it's not possible to maximize all of these at the same time. First is wavelength data rate. Then we have line card capacity, total fiber reach, and optical reach. Now, the last 2 are the most obviously difficult to maximize at the same time, because when we increase fiber capacity using a given transmission technology, we'll inevitably reduce optical reach and vice versa. The optical industry has found 3 different axes of optical scaling. We can scale baud rate, increasing from today's 33 gigabaud to 66 gigabaud and then onwards to 100 gigabaud. We can scale modulation order. And today, QPSK is probably the most common modulation type, but modern implementations provide 8 QAM, 16 QAM, and in future very high order modulations that include a technique called constellation shaping to squeeze out every last fraction of a dB from the fiber. And finally, we can scale the integration level. This last axis is probably the least familiar to you if you're not familiar with Infinera messaging. What we mean by this is the ability to integrate the hundreds of optical components for multiple wavelengths onto a single optical chip, the famous photonic integrated circuit, or PIC. Scaling baud rate and modulation will, for example, increase the capacity per wave, from today's 200G to 600G and even 800G per wave. These 2 axes will also scale line card or appliance capacity, but so will integration level. In essence, we go parallel using PICs and can scale capacity per device in a linear fashion. So let me pause and just emphasize a very key point here. Of these 3 axes, our competition can scale along the first 2, baud rate and modulation. In a separate tutorial on optical leadership, my colleague Jay Gill will explain why we're able to do better along these axes. To give you the quick version, Infinera is the first DWDM company to adopt a technology called Nyquist subcarriers. Now, our competitors could do this too, but we are the first to do this, and the odds are that we'll have a 2-year head start on them. But when it comes to the third axis of integration and PIC technology, we really are way ahead of the rest of the market. Once again, Jay will explain why integration can give us an advantage in terms of optical performance, something that's been demonstrated over and over in the past year since ICE4 has been shipping by a number of really amazing subsea field trial results. Subsea really stretches an optical implementation to the very limit, and ICE4 is not only beating our competition's current generation solutions, but we've been told that it's getting very close to the performance that CINI and Nokia are promising for their next generation chipsets. And these won't be shipping in real products until mid-2019. For the moment, let me just remind you all about a key difference that integration brings to our cloud solution. If we look at our competitors, this is how they would deliver 1.2 terabits of capacity. In other words, one 200G transponder at a time. This is the classic pay-as-you-grow model that's evolved in the optical industry over the past 3 decades. With Infinera's PIC-based solution, the whole 1.2 terabits per second is delivered in one chunk, with one installation operation in the same time it takes to install the 200 gig transponder. The capacity is ready for services to use it right away. So that leads me into the next section. Given we have pre-deployed capacity in the network, how do we make it programmable? You can see the shortcoming of the classic transponder approach here in this simple point-to-point example. The fastest client interface speed today is 100 gigabit Ethernet, so I'll use that as the example, with traffic growing to fill the 100 gig wavelength. Because routers do statistical multiplexing, we could add more than 10 gigabit Ethernet services, but we run the risk of quality of service problems if we do that. Now, at some point, we decide this 100 gig wavelength is definitely full. That's the moment it's time to send an engineer in a truck to each endpoint of the fiber to install more transponder capacity. And our simple philosophical statement is therefore that transponders and the programmable network are like oil and water, because whenever you need a truck roll, you have a barrier to automation. A few slides ago, I described the 1.2 terabits per second of capacity you get when you install a PIC-based appliance or line card. But what if you don't need all of that capacity on day one? Well, back in 2012, Infinera recognized that not all of our customers need the big chunks of capacity that PICs enable right away, but they almost always grow into that capacity very soon. So we needed a mechanism to allow us commercially to install the full capacity initially, but for the customer to be able to pay for chunks of it at a time. So here, for example, there's 200 gig of the 1.2 terabits per second active. The customer can turn up a couple of 100 gig e-services over that capacity. But the rest of the capacity is already installed, and with a click of the mouse on the network management system, it can be brought into service. We call this commercial idea instant bandwidth, and it's totally unique to Infinera. Customers love it because it allows them to respond to unexpected service demands, but still keep their networks as cash flow efficient as possible. We've had instant bandwidth for a while, but with ICE4, we introduced sliceable photonics. What that means is that instead of the whole capacity of the PIC having to go to the same destination PIC, we can slice up the different wavelengths using a ROADM. Now, when you combine that with instant bandwidth, you end up with the ability to add capacity incredibly quickly and to direct it where it needs to go in very granular units. Once again, sliceability is unique to Infinera, and customers really love the idea. But this section is about programmability. Instant bandwidth is great, but in a programmable network, you need the ability to not only add new capacity to a given route, but also to take capacity away and put it somewhere else in the network if demands change. Now, the original instant bandwidth model didn't allow for that because it was all about rapid service activation and capacity growth on individual routes. Most recently, Infinera has introduced instant network. Now, there are three basic differences between instant bandwidth and instant network. First is the scale of capacity in a unit. So we're now in the 1.2 terabits per second or even 2.4 terabits per second range per module, per appliance, per line card, and so on. Now, second is the introduction of sliceability, which I described just now. And finally, we have this idea of totally flexible licenses and the idea of license pools. So let me spend a couple of minutes describing the license pool concept. One of the biggest barriers to a concept like instant network is the idea that customers will be effectively returning product to Infinera. Now, that would play havoc with our revenue recognition process. So with a terabit scale capacity installed in the core, we create the idea of a customer license store. Instead of buying licenses that are tied to individual modules, these licenses can be moved to any link where there's spare capacity. So let's say, for example, that we need capacity between A and B. The license is taken from the store and applied in seconds to the pair of devices. Services can be turned up right away, and the network operator can start to bill the customer. Now, here's another example from B to C to D. Now, this could be a hop right through the ROADM, in which case only one license is needed. Now, here we do the same for A to C to D. But now there's some service churn. The AB capacity is no longer needed, and so the license is returned to the license store. There are no truck rolls needed, which means that this whole process could be orchestrated under software control. Extending instant network outside of a PIC-based implementation is a challenge, obviously. But we can take pointers from our competitors who do a similar thing on a very simple scale, just selling 100 gig or 200 gig of capacity on a 200 gig capable transponder. So instant network can be extended into the XTM2 family in the same way. Now, combined with the XTM2's extremely efficient power per bit and compact size, it makes it the perfect platform for fiber deep installations in next generation cable and mobile. So the end result of instant network and sliceability is a highly programmable optical network with the ability to turn up instant capacity without truck rolls. So I've explained how Infinera's PIC technology can help maximize core network capacity and also to create a truly programmable optical data plane in the network. I'd like to end with a look at how we could add intelligence in this architecture. So first of all, why do we need to add intelligence? In the past, networks have just been run by humans, so why change that now? Well, the problem is, with humans, Well, the problem with humans is that we slow things down, and we tend to make mistakes. So we need to automate network operations to avoid those errors and to speed up service delivery. Now, put that against the background of cloud-scale architectures. Content providers like Microsoft, Google, and Facebook operate their data centers using virtual machine architectures. Every day, each of them are creating and destroying about 1 billion virtual machines, and the only way they can do that is to allow the whole process to be driven by machine orchestration. Now, if we look at it in a wider context, it's that same level of scale, which means that traditional network operators also need to care about automation, or they risk an unmanageable level of network complexity. We see rapid pattern shifts driven by device and user mobility, the move to fiber deep changing the face of next-generation cable, and powering the 4G to 5G evolution. We have the Internet of Things, which is where billions of machines talk to each other into the cloud. We have virtual reality and device autonomy. In particular, the volume of machine-to-machine traffic has already begun to dwarf user-to-network traffic volumes. Now, if you talk to almost any network operator, you'll find they're really worried about OPEX, which can be running at 2 to 5 times the CAPEX cost for the network because of the difficulties they have in automating operations. They have to be able to manage network complexity, especially when users are demanding lower costs and faster timelines for service delivery. But how could this happen in an evolutionary way instead of just transforming things overnight? Every customer will be different, but let me outline 3 obvious phases of how we could apply intelligence into the network. So let's start with an Infinera network that delivers the unique instant network capability I just described. There'll be a network operator, and they'll be responding to service demands from a customer. Now, these could be 2 different companies, or they could be different departments in the same company. To create a new service, a human in the customer talks to a human in the network operator, who will then generate the capacity change in the network. The actual protocols driving that change could be from the network management system like DNA, or it could be an SDN platform. Now, to be honest today, it's more likely to be an NMS, but some operators are rolling out SDN. But the power of instant network is that it can respond instantly to the changing demand without the need for transponders to be ordered, shipped, installed, and tested before the service goes live. Okay, let's evolve the network. As before, we have a customer and a network operator. This time, a human in the customer talks to a self-service portal in the network operator, and that acts as a front end to a capacity planning system that has a designated and limited ability to turn up capacity in the network. Those limits are imposed to give the network operator a comfort factor as they get used to network automation. The back-end systems provision the instant network capacity, and it's now more likely that this will take place using SDN than using an NMS. This approach reduces operational costs, and it can scale to large numbers of services and is popular amongst users because they feel they have more control. Okay, the final evolution. An artificial intelligence process, basically a machine, in the customer network will decide that new capacity is needed. It will talk to an artificial intelligence process inside the network operator, and this will generate the capacity change. Now, it's almost certain that this type of process will use SDN, or maybe even whatever comes after SDN as the network control channel. The key message is that instant network provides the underlying foundation for this evolutionary change. The software and processes above it might change, but instant network and the underlying PIC-based capacity are a constant. As a result of our industry-leading capacity and our unique ability to create a programmable optical data plane, Infinera has an amazing SDN story. We've chosen an open-source SDN platform in the form of Open Daylight for our Exceed product. We've championed open APIs across our whole product line and have taken a lead in areas like our Open Line System and Open ICE capabilities. And we've insisted on open, published information models to ensure that third-party developers can harness the full power of our solution. Now, we know that these choices have helped our customers accelerate time to market for their new services and applications. But what we don't have is a network orchestrator. For a long time, this was a conscious decision on our part when we saw the lack of success of orchestrators like Blue Planet, especially given the eye-watering amount that Ciena paid for CINI networks. A key capability that Corient can bring to our solution is the Transcend Maestro multi-domain orchestrator and the experience you've had in pushing that product into the market. In summary, cloud scale requires 3 specific properties from a user solution. These are capacity, a programmable optical data plane, and intelligence. Infinera has a unique and better solution for capacity based on the outstanding performance of the ICE4 chipset. And although I haven't mentioned it in this deck, we have a very strong technology roadmap for future ICE generations. The combination of the service-ready capacity in ICE4 and the commercial innovation of Instant Network created the industry's only programmable optical data plane. And it's clear that the innovation and development work done by Corient for the Transcend Maestro solution can take us a long way to delivering the intelligence needed by cloud-scale operators in their next-generation network architectures. Thank you for your attention. Please check out the other training videos that will fill out the details of our outstanding optical performance and the Infinera product portfolio.